In this video, we're going to look at Section 3, Position Time Graphs. And you can use a position time graph to determine an object's position at a certain time. That is going to be our main idea in this section. So in this section, we're going to answer three essential questions. First, what information do position time graphs provide? Second, how can you use a position time graph to interpret an object's position or displacement? And third, what are the purposes of equivalent representations of an object's motion? So a few new terms that we're going to look at here are position versus time graph and instantaneous position. Also, we'll talk about intersections, but that should be an old term from your math courses. So when finding a position in a position versus time graph, the time data is plotted on the horizontal axis, and that's typically how we want to write it. Especially when we say position versus time, that means y, or vertical, versus x. And so we put the time on the horizontal axis and we put the position on the vertical axis. When we graph an object's position, it helps to give us a physical representation of what's going on with the motion. And a lot of times the graph is much more helpful or much more useful than just watching the motion itself. And the symbol X represents the instantaneous position, and this is important, instantaneous position of the object. And that means that it's the position of the object at one particular instant. So at exactly 2 seconds, what is the position of the particle? And according to this graph, it's at a position of 10 meters. So we're going to talk about 4 ways to represent motion. First, we're going to use words, then motion diagrams, data tables, and position versus time graphs. So to think about this, words, how would we use words to describe motion? Well, we could say that an object is moving to the right, or an object is moving at a constant rate, or an object is speeding up or slowing down. So these are all words that we'll use to describe motion. Motion diagrams can help us with this by seeing a series of dots or dashes, and if we see those are getting farther apart, well, then we can see that, all right, that object is speeding up because the space in between is getting bigger with the same time interval. Data tables can help us to see this sometimes as well, looking at all of the data at a particular time, given the position, and we typically like to turn these data tables into position versus time graphs because those give us a much better physical representation of what the object is doing. So let's take a look at this problem here as an example. And we have a position versus time graph over here on the right, and we have a graph of Juanita and of Heather. And we want to know, where was Juanita at t equals 1/2 hour, and at what time was the magnitude of Heather's position equal to 2 kilometers? So these are 2 different types of questions. First, we're given a time and we want to find a position. The other one, we're given a position and we want to know, when did that occur? What time did that occur? So we can actually answer both of these questions very similarly. First one deals with Juanita. So we're going to look at this green line here corresponding with Juanita, and we look at 1/2 on the time axis, go up vertically and see where that intersects with the green line, and then go across horizontally and see that that's about 2.5 kilometers. So that's halfway between 2 and 3, so we'll say that's 2.5 kilometers. So to answer the question, where was Juanita at t equals 1/2? She was at 2.5 kilometers. Well, going to find Heather's time when her position is equal to 2 kilometers, we do the same thing, but now we're going to start on the horizontal axis at 2 and come over to where we intersect and then drop down. So that's going to happen at about t equals 0.8 hours. The nice thing about position versus time graphs is we can actually graph multiple objects on one position versus time graph, just like we saw in that past example. This gives an example of 4 different objects that are moving position versus time, and we can conclude a lot of things based on these objects, but we're not going to get into all of them. The key is when they intersect, when the 2 lines intersect, that means that the object is at the same place at the same time, the same point in time. So for instance, right here at this intersection, that's when object C and object D occupy the same position in the same amount of time, or at least the same point in time. So let's use that concept to look at this race where we have Luis and Ty racing, and we want to know, when does Ty pass Luis? And so we know Ty is going to be positioned behind Luis at the start, because if you look, Ty doesn't leave until 10 seconds after Luis does, because at t equals 10, Ty is still at the origin and then starts to move. Well, Ty is moving more quickly than Luis, and at some point they intersect, and that's when we get the pass. That's when the pass happens. So we have to look at that intersection point, and we see, well, that intersection point happens at 20 seconds, and at the position of 40 meters from the origin. Hopefully you're able to answer these three essential questions and you have a better understanding of the vocabulary after this video.